PhD in quantum mechanics from, I think, TU München, I think.
Yes,
yeah,
exactly.
There you go.
Yes.
And she will talk about quantum technologies, the next Gen AI in finance. Over to you, please, Martina.
Exactly. And actually co-leading together with Henning Soller, we also have him here, and he will take over the second part of the presentation.
Okay, no problem.
We'll do that together.
Thank you.
Cool. Okay, then happy to kick us off. So recently we got a lot of questions around when will Q-Day actually happen? How should we prepare from an industry perspective? And also which industries will actually be affected first? So this is why we will look at the following topics here. So first, we will see a little bit of a broader market perspective and also investment perspective. So where does the industry stand at the moment? Targeted a bit towards the financial industry and also setting a bit the scene, what is actually the motivator behind quantum in finance. And then we move on to what is actually the value at stake in finance. So where do we see the highest potential in the different business units of a bank, for instance, and what are the use cases that we think have the highest impact in the near term and also in the long term. And then we will also move to an example, actually a very concrete one, of a quantum use case in finance that also banks are interested in, and it's relevant for banks. And then we will close with a short outlook and some recommendations and next steps, what we see is important for the industry. All right, so given that we get all these questions around Q-Day, when things are going to happen and what kind of next steps need to happen to reach a fully fault-tolerant quantum computer, we at some point put this on a timeline, and this is a very busy page, so let me walk you through. So Q-Day, the actual day where we see a quantum advantage or a significant cryptographic algorithm actually being broken. We always said it's around 2030 plus minus 1 or 2 years. If we now look at the recent roadmaps and the quite ambitious roadmaps that you also might have seen from the respective players, we see this shifting a little bit towards the right, towards the left actually, a bit earlier. So it's rather 2020, 28 than 2030, looking at the recent roadmaps. And then when we look at the different functionalities that actually need to be enabled, then obviously at the moment we have proof of concept level. So this has been shown. You might have also have seen the recent announcement by HSBC and IBM. People are actually working on that, and the proof of concept is there. However, the killer application in finance, but also broader across industries, is still missing. So the next steps that need to happen is like the proper hybrid integration, that we not only leverage the quantum computer, but also together with classical high-performance computers. And then after that, basically reach the quantum advantage for real-world problems. And then after that, we can actually scale it. And for that, we not only need scalability of the underlying qubits, but also the respective algorithms, and in particular, the error correction. And during my PhD, I actually worked on error correction myself, and it's just very interesting to see also the advancements in the field. I think we're not there yet, but we go with big steps ahead. And then why finance? So you can see at the bottom that at the moment, there's a lot of traction from governments and also national defense. But then one of the first industries we believe will be finance in terms of adoption. And during the talk, we will also see why it's exactly finance, both from a computing and use case point of view, but also from a security point of view. Another motivating factor is actually the question, why now? So why is it relevant that banks and also quantum players work together on use cases now? So when we look at the recent breakthroughs or recent announcements from research, but also from the quantum players, we see a lot of focus on the stability of the qubits and the computers, plus also on error correction. And this is actually interesting because then we can tackle the problem from both sides. So not only the scaling of the physical qubits, but then the better the error correction codes get, as you know, then we can also approach the problem from the other side, that we need less resources. And this is then also reflected in the publications and patents. And this here on the right-hand side is not only computing, but also communication and sensing. And there is quite an uptake also in patent applications, which is a good indicator of a lot of traction and momentum in the field. When we look at the investment landscape, like 1 or 2 years ago, we had this dip in investments, and then people started thinking, okay, is now the money actually going out of quantum? What is happening? This is actually not the case, because we saw an increase thereafter, which is actually a very good sign. However, also the composition of the financing shifts a bit. So we have around 2/3 now of private funding, and then we have 1/3 of public funding. And this is actually a 19% increase compared to the year before. And this is also due to a lot of governments gaining interest. We have this more than 7 billion deal of Japan, actually. There are a couple of other countries that invested heavily in quantum, or at least announced investments over the next couple of years. So this is a bit like also fueling the industry. And then a very interesting shift that we see is we move from proof of concept, that is at least what we see also when working together with industry players. We move from proof of concept to co-development of use cases. And hence, this also means revenue for the quantum players. And you can see that we actually have a 40% increase of revenues. And the forecast is actually very promising in that regard as well. And the cool thing about this is this co-development of use cases, that the expertise of the banks and of the financial industry comes together with the quantum knowledge of the startups. And this is a very interesting moment in time, I think, because the true expertise for the real problems that have impact in the industry is actually coming from the banks and from the financial industries, and then the quantum computing aspects from the quantum player. So I think this is a very important moment in time where we need this collaboration. And then eventually, when we look a bit forward towards 2035, we actually estimated a 1 to 2 trillion opportunity of potential economic value. This is not only finance, but this is also broader all industries. And this is also now leading us to the second chapter, which is the value at stake in finance. And here you can see the financial services industry actually on top. We estimated the economic value short term, which is 25-30, the first column you can see. And then we have the 2030 to 2035 long-term estimation. And here we can see the value at stake, basically, that was estimated when you go through the different units of a bank, and then you look at the use cases, and then we did an estimation of how much impact quantum computing could actually have across the banking units. I'll come to that in a second, because we have a little bit more of a deep dive here as well. But you can see that it's across industry, quite a big potential across or for the economic value. And finance is, we believe, at the moment, the biggest one. Speaking about tackling this from both sides, so I also wanted to bring in the security aspect here a little bit, because it's super important for banks. And these curves actually show the moment where we might have Q-Day. And this is basically this box that you can see. It's a several years time frame, because no one can actually predict it for sure. But we can see that there has to be a moment where we have the physical qubits and the scaling of the physical qubits on the one hand. But then on the other hand, we can also have a look at the resource requirements to break certain security algorithms, like, for instance, the RSA. And the better the algorithms actually get, the less resources we need for that. And this is somehow how the curves come together and then eventually hit Q-Day. But it's super important to say that it's not only the physical scaling of the hardware, but it's also a lot of unlock potential in the algorithm part of things. And speaking about algorithms and security, we can do the same thing, and this is not exhaustive. This is just like a small selection of industries. We can do the same thing actually looking at cryptography. So we looked at the cryptography requirements. These are quite high for the financial industries because there is just a high demand for secure communication, very sensitive data. Then we have quite a high crypto agility. So basically, how agile they are with their cryptography and how agile they can also react, how modular this is all set up within the bank. And then we looked at the Q-Day impact, and the Q-Day impact is also quite high for finance, just due to this diverse and highly distributed infrastructure. And this also actually leads a quite high adoption likelihood for QKD, and not only PQC, but in particular QKD in the long run. And when you compare this with other industries, you can see pharma at the bottom that is a bit similar than finance for the Q-Day impact, but we see the highest ones here for finance as well on the crypto side. When we now look at the impact and what actually the quantum technologies can impact within the use cases, then we have 3 different dimensions. So one is cost reduction when you look at it from a business perspective. Then quantum computers can enhance the accuracy, for instance, of the underlying model you're looking at. And then in the end, this actually leads to cost savings. Or on the other side of things, you can have an acceleration, so for instance, because with your quantum computing enhancement, you can actually work more efficiently, and then you could have a speed up due to the parallelism, and then you end up with an acceleration or revenue enhancement. These are the 2 categories that are mostly looked at the moment, I feel. Also, when you look at the use cases that banks and quantum companies work together at the moment. However, there is a huge third bucket that is sometimes a bit overlooked, which is the new business opportunities. And this is quite a high value potential, I would say, because there are completely new use cases. When you think that through, then you can think about with the new level of quantum security we will reach at some point, is the regulation we have within the financial industry really necessary? Or is there a completely different system we might want to think about? And then there are use cases like quantum money, for instance, you can think through, and it gets a bit into the fancy side of things, but still, I think this is a very important bucket that should be kept in mind. Now, when we look at the categorization of the use cases, most of the time, people categorize them by mathematical problems. So then you can say, okay, this is a linear algebra problem, or this is a simulation problem, and then I do credit risk modeling. So in the end, this is in the bucket of simulation. Or you can have a mathematical optimization. So for instance, with collateral optimization or portfolio optimization. So then this would fall in the category of optimization. And then you would also have factorization, like could be these kind of categories, could be different ones, but most of the time people structure it by the mathematical problem. And you can also see publications. I'm sure you have seen some of those. So what we did is actually we took a different approach, and on purpose a different approach, because we're working with banks, with industry players, and they don't necessarily think in mathematical problems. They rather think in units and business units of a bank, which is why when we looked at the value at stake behind the use cases in finance, we looked at the different business units of a bank. So this is corporate banking, this is cyber, this is retail, payments, asset and wealth management, and investment banking. So these are like the standard business units that every major bank basically has. And then we looked within each of these business units basically at the very compute intense use cases. So what are the use cases? Could be heuristic and with a huge high compute potential, or the actual compute intense use cases. Where are those? And then afterwards, we looked at actually the impact on the revenue or in the cost, because in the end, it's either a revenue enhancement or you can save costs with it, to put it very simply. And then we estimated how much impact a quantum computer could actually have. So is it a 20% or 30% increase of your revenues? Could you actually save 10 or 20% of your costs with a quantum computer? And that's basically how we came up with these numbers for the value at stake for these different business units. And we do have aggregated benchmarking data basically behind that from the major banks. And this is how we looked at the use cases from more like the business and the value at stake lens instead of the underlying mathematical problem. And now we can go a bit more in depth into these use cases. This is a very German McKinsey slide, very busy. So let me walk you through. We have exactly the same business units of a bank, basically from corporate banking to investment banking. And then when we look at corporate banking, for instance, first. So when you actually deal with corporates as a bank, this can easily get quite complicated and quite complex. A lot of things to handle, a lot of variables. So this is naturally something where the quantum computer can shine. And then we looked at the different impact levers. So would it actually be a cost reduction? And in the case of corporate banking, you can actually optimize the collateral allocation, for instance, and then you can save costs. Or is it actually an acceleration potential? So for instance, when you can have real-time product decisions, so then this would be an acceleration aspect. And then you also have new business opportunities for the corporate banking, which is, for instance, communication for trade finance in a very secure way. But then there's not only the impact that you can have in form of like cost, revenue, new business, but there's also the main tool that is required. And here, for instance, with corporate banking, you need the computational power for the multivariable optimization of the respective task. So this is naturally something where we run out of classical compute capacity and where the quantum computer just naturally can come in. And this is very different, for instance, when we look at retail banking in the middle, because this is just by its nature simpler in terms of individuals. Simpler, I mean, individual is like simpler as like a corporate bank. However, when you then go to high net worth individuals, for instance, which then sit at asset and wealth management, this becomes better in terms of quantum then again, because this is naturally a bit more complex. And then you can also think about personalized pricing or more efficient portfolio allocation. These are a couple of examples on the use cases we had looked at and how the different business aspect comes together with the main tools and the quantum computer in the end. And maybe one aspect before I hand over to Henning then to have a bit of a deep dive for collateral optimization. One message we wanted to bring across around PQC and QKD. Because when we look at the current regulations, we see a strong focus on near-term PQC, which is, as you know, like software-based. It's a bit easier when you look at the total cost of ownership. It's a bit easier when you look at infrastructure requirements. You might need a hardware upgrade if you work on a legacy one, but it's very different from QKD, where you actually need a different hardware. But it's very interesting because the industry is not there. Like the industry is indeed preparing for full quantum security and fully mathematically proven quantum security, which is then QKD. So that's something that we wanted to share as an extra message. And now when I hand over to Henning, maybe one thing we saw when we talked to banks, we saw a lot how important it is to bring business where the real problems sit and where also the impact will at the end then be together with the quantum experts to really unlock the potential. And how we can unlock the potential, Henning will tell you.
And maybe sort of when we go now a bit deeper, sort of also on the quantum use cases on the finance side, sort of we will go a bit deeper specifically on one use case around collateral optimization. But before we do that, we want to illustrate a bit sort of what we currently see and what are some of the questions that we're also currently trying to answer. Because number one, sort of we all know that a number of NP problems can indeed be solved on a quantum computer. And of course, there are a number of P problems that are very relevant in industry that people are also solving to date. But number one, there is a big question out there in terms of, is there like a practical algorithm that one can use for post-quantum cryptography that will actually pass the test of time, that will be practical and that can be used and also for purposes in order to have an algorithm that essentially makes PQC an actual reality that can never be broken. That is one question that is open. The other question that is currently open, at least from everything that we see, is the question, is the quantum computer already the end, sort of to the technological evolution that we would essentially see on the algorithmic side, or are there further advancements that one can make? Because what we essentially see with all of the problems in terms of the NP problems that we really see in industry, there is a big question whether there are practically relevant problems that cannot be solved on a quantum computer, at least sort of with the means and with the knowledge that we would also have to date. And you already see that there are, of course, a number of questions in here that are mathematically not very well defined. What is a practically relevant problem? and sort of what is then the overlap between the NP problems and the problems that a quantum computer can reasonably solve. Those kinds of questions are relevant, and indeed sort of those are also mathematical questions that we will need to answer at some stage, and will also require to work together on what some of these rather undefined words in this terminology then also mean. If we now go a bit deeper into what essentially is then one very practical problem that can also be solved on a quantum computer is the wonderful problem of collateral optimization. And I'll go with you through a very quick description of this, because typically, if you look at collateral as a private person, it's very easy, because typically you get a loan and you get this in exchange for a house or an apartment. And then sort of there is something which is the collateral, and there is a loan, and there is a one-to-one relationship. And then sort of this is quite an easy one. If you're a company, this kind of relationship can be rather difficult, because there are a number of things that can potentially be accepted as a collateral that are not just a house. So you see here like physical gold, goods in circulation, transport vehicles, aircrafts, whatsoever. And there are a lot more loans that you typically also have if you're a corporate. You may have like actual credit lines, you may have certain accounts receivable, you may have certain guarantees, credit cards, whatsoever. And oftentimes, it's also not okay, like I can put any kind of collateral against any of the respective loans, because as an example, there are certain loans that are actually secured by the state, and only certain types of collateral are accepted in order to get these specific conditions then also by the state in order to be protected, for example, if you do foreign transactions. And so therefore, what this in essence becomes is a very big matching problem in terms of how do I match all of the respective credit lines with all of the respective collaterals that I possibly have out there, and how can I maximize the actual possibility of, for example, now financing an additional residential property, an additional product line, and so forth. This kind of matching problem, if you illustrate this also a bit more on the next page, is of course something that is ideally suited for a quantum computer. It's a problem that as a matching problem sort of is definitely within the class of the NP problems. Second is it is a problem that in principle requires a lot of considerations, and therefore is ideally suited then also for parallel compute. And it's a problem where we also have the possibility of essentially looking at the problem also as one of the most complicated problems that we would also see in industry, because oftentimes you have like 50 lines of credit and you have at least 50 different kinds of collateral. So it's also practically a problem that currently cannot be solved efficiently with the present means that we would have available. And so what we essentially see, this is one of the examples of like a practical problem that can actually be solved on a quantum computer. And there are many more of those problems. If we also look at the next page, you see that we've looked at what are all the banks that are also working together with the respective providers of quantum compute capacity. And you see it's not just that they're working together in terms of figuring out sort of how to use the machine and work on the respective hardware, but that they are also working together with the software players in order to identify first algorithms and first means to also solve practical problems, be it derivative pricing or be it collateral optimization. And they do this not just for the purposes of testing things out, but already in order to generate IP and to build capabilities in a space that they also deem relevant for their future competitive advantage. Maybe if we just once go to the next one, what we see is that there have been a number of collaborations established also between banks and these respective problems that they have solved, and then also together with the respective providers of quantum compute capacity, solving those problems already today, practically on a quantum computer. So number one, we see that people are presently already working on these kinds of problems. Oftentimes, we also see that IP generation is key as part of this. And we also know that there will definitely be further use cases and further applications of quantum computing then also going forward that we will currently not already see. And so therefore, just closing quickly, maybe with a very quick outlook at the end, and then I think we also have time for maybe one or two questions at the end. Number one is we want to say, take action now, because it will be required to now build the relevant capabilities and to now also generate IP within that space if you want to have competitive advantage as a bank also going forward. Second is there is the possibility to already capture value to date, because the quantum computer will definitely have a competitive advantage going forward, plus the ability to reduce the risk, for example, of harvesting data now and sort of being able to decrypt it later. There is a business case already today for the respective banks to essentially engage on this topic. And finally, what Martina also earlier mentioned, sort of do not stay confined to one specific business unit where you essentially want to try out quantum, but sort of include all of the relevant business units. Because also when we started, we did not think from the onset that corporate banking would be the most favorable business unit within a bank in order to employ a quantum computer, but definitely it is the one that simply has most of the business and therefore also most of the complicated applications that are actually suited for a quantum computer. Let me maybe just quickly stop here, and I think we have time for a few questions if there are any.
Thank you very much, Dr. Soller. Thank you. We have any questions? Let me see online. Any questions online? No. One of the things they did ask before, I don't know if you if that would be okay, that some would want your slides, but I don't know if that's okay. That's a no, then, from what I can see.
No, I think we will just need to see sort of that we're not revealing any information that is
okay.
critical. So Martina and I will clean that up, but sort of this we can make happen. No worries.
Okay.
Like it's not that we have like these super massive secrets here. We just need to make sure that it's not sort of something that is super controversial or something. Okay.
Well, there are no questions. I think this is not because it's not interesting, but because it's late here. It's very late in Germany, probably, because I should shut up, right? I mean, it's like 10:30 probably. No, what is it? Yeah, 10 o'clock. But I thank you very much.
11 p.m. in the evening, so you can.
Okay, so fantastically scandalous that
you're the last call before being able to sort of get into proper clothes in the evening.
Oh, I have no argument at all here. We hope to see you here tomorrow also. Thank you very much.
And if you have some questions, feel free to reach out.
Thank you. Thank you very much. Thank you.
Thank you.
Thank you. Bye.
So tomorrow morning we are starting at 10 o'clock, and our first talk is world-class economist Erik Hazels, who is a very famous econometrician, and that's 10 o'clock, and then we'll have. So I hope to see you all tomorrow. Thank you. Thank you for coming.